I'm John Light from the Intel Open Source Technology Center, which is where the other names like Ostro and Zephyr and Yocto and so forth come from. I'm not here to talk about any of them directly. This talk was inspired by working for the last year on a major IoT software project. And I discovered that the issues that I found in this talk were really not understood by anybody else in that project. And so I wanted to share the issues here today. And I don't think we're going to solve the issue generally, but I think it's an opportunity for people to understand that there are issues like this that need to be solved in the IoT realm. Embedded software, interestingly, is in spite of the name of this conference, is actually not used a lot. And a lot of the people who have done embedded programming are either leaving the field or they've done stuff over the last 20, 30 years that and their skills are being lost, apparently, from the evidence that I've seen. And the irony is that these skills are being lost just as IoT has started an explosion of highly constrained computing devices that need these skills. So I just want to make sure that the people who do IoT have a clue of how important these skills are. Now, I wrote these slides a little bit, there's a lot of slides and they're fairly complex, and I'm not going to go over all of them because there's not enough time. I wanted to write it so that since there's 9 tracks, people who can't attend my talk can get most of the content and the idea of the talk without so I'm not going to cover everything that's in the slides. Here in IoT, we talk about millions and even billions of sensor devices, actuators out in the world, and the question is, what do those look like? Well, one thing they look like is they're typically very power constrained, and they are necessarily very cheap. And because they're a term that was used in the early 2000s are smart dust. You just take a handful of these and toss them into the environment. Now, I don't think that's actually going to be done, but it's a good metaphor for how tiny and inexpensive these things need to be. And when you get that tiny and inexpensive, they need to be have very few resources in the chips so that they're very cheap. So in this talk, I concentrate on 2 issues of embedded programming: memory handling and coroutines, although I don't know if I'll get to coroutines. But the key I want to explain is that in the past, when there's been a resource constraint, there's always been an assumption that Moore's law will save you. If there's not enough memory, next year there's twice as much memory. If there's not enough processing power, next year there's twice as much processing power. So don't worry about constrained resources. And I'm here to suggest that for several reasons, the constraints we're seeing in leaf nodes, the small devices that are on the periphery of IoT systems, are not going to, the resources are not going to change dramatically in the at any near future. And we're going to live with those constraints, so we better be able to deal with them. And then I'm going to cover a number of myths associated with memory management that make some of this worse. And I'm not going to talk about the details of embedded programming, choices of RTOSs or development environments, things like that. So here's an example at Intel of an IoT processor. You can call it the Quark, it's the processor that's used in the Curie SoC. notice the equivalents are all in late 80s and early 90s. So there's very, very low-level resources. But what distinguishes these devices is not the computing resources, which are adequate for most of the jobs they're being put to, but the peripherals that come on these chips. So I'm just going to, so the sleep modes, the sensor hub that can keep track of various sensors, and including sensors like this one comes with an accelerometer. And interestingly, it comes not only with an accelerator, it comes with a neural net to do pattern matching in the accelerometer. A lot of analog comparators and battery charging circuit and Bluetooth. And these are all things, whether it's Bluetooth or not, it's some communication mechanism. All these things are things that are going to be in these small processors and are going to take up resources, take up chip area. So the first myth is that IoT devices will use the latest technologies. Well, it doesn't. It turns out that because you want these things cheap, they're always going to be a step or two behind the processors that we use on our desktops. Another myth is that Moore's law will solve the resource shortage. The problem is not that Moore's law isn't going to continue, and it is for some time, but the issue is what is going to benefit from Moore's law. Now, this benefit historically has been in standard computing resources, CPU speed, memory. But in the future, in these physically constrained devices, I submit that Moore's law is going to be used to create more sensors, bigger neural nets, and more communication devices, and better communication devices. And also to make the devices smaller and run with less power. And if you have those goals of capability and lower power, you're unlikely to spend those resources on getting more RAM and more processing power. Here I'm just pointing out that in embedded programming, memory usage design is critical, and that I'm hoping if you walk away with thinking that memory design is critical, I will have accomplished a lot of my goal. The biggest problem with memory in constrained devices is heap failure. Heap failure is the inability of the heap to supply a required allocation in spite of having enough memory. Now that's different than running out of memory. It's saying that the memory isn't available. And when this happens, the malloc fails and the program typically stops. And it's also problematical what happens when this happens. So I'm going to go into those a little bit. So here's the heap failure is usually the result of fragmentation. Now, here's an example of a tiny heap that has 1,024 bytes in it, and it has a single 13-bit allocation in the center as a result of dynamic mallocs and frees throughout the running of the program. And yet, although there's over 1,000 bytes available to allocate, a 600-byte malloc will fail. And you may think this is contrived, but I've seen this before, and I've seen it with much larger heaps than this. The problem is that in the allocation of memory if there's a lot of mallocs and a lot of frees, the allocations can stochastically make amazing patterns. And I've spent a lot of time stepping through heaps in core dumps and seeing the amazing structures that can happen in a heap. And the result that large allocations fail even though there's lots of memory to support them. And the symptoms of a heap failure, unfortunately, are often very, very hidden. And so I'm going to go through these very quickly. In desktop PCs and in server PCs, you just got huge amounts of memory, and you don't even notice heap failures, because if a heap failure occurs, you just allocate more memory. And this is easily done in a virtual memory environment. And this is one of the major causes of bloat. Now, bloat can also come from memory leaks, where people don't free up what they're allocating. But it can also exist because even though there's space available in the current heap, an allocation can't be made, so another page must be allocated to satisfy the heap, satisfy the next malloc. And then you just keep doing this and keep doing this and keep doing this, and even though there's lots of memory available, it's not available for the next malloc, so you have to allocate more space. Now, in a constrained device where there's no memory management, where there's not no virtual memory, this shows up typically as a failure. And we all know to test the results of a malloc to see if it fails. But what happens when you test that? Very often you want to report it, and the process of reporting gets more malloc failures. And very often malloc failures cascade to the point where you don't even know what happened. The device stopped working, and you have to work really hard to actually report it. And of course, rebooting, just fix it. And this is one of the cases where, oh, well, we just restart it and see what happens. And so heap failures can be very insidious. And the other problem is that they can happen over a long period of time. Whoops, go the other direction. So here's a myth. Fragmentation results from calling malloc, and the answer is no, it results from calling free. So it's okay to call malloc in an embedded environment, constrained environment, but you just don't call free. And that way you get your memory, you just have to manage it more interestingly, and we'll talk about ways to do that. A myth is memory management hardware helps. Having an MMU doesn't help this problem. It's simply, the real issue is that the heap is a single contiguous range of memory, whether in virtual space. When if virtual space is the same as physical space, then, which is the case without virtual memory, then it still can be fragmented. Virtual memory solves the problem on large computers because you allocate another block and extend the heap. But that doesn't work on constrained devices. Bonus myth here is that, no, that's just a different way of saying the same thing. Testing doesn't solve the problem either. The problem is that typically, I mean, it's important to test. I'm not putting down testing at all. You need to test. I'm saying it's necessary, but not sufficient. The problem is that heap allocations get fragmented over time, and the time can be in large time scales. So for instance, you could test it for hours, weeks, and the problem is that the memory fragmentation can occur over months or even years. And if we're trying to build devices that can go out into the environment and work for long periods of time, we have to be concerned about whether there's going to be memory fragmentation. And I'm saying testing doesn't prove it's not going to happen. In fact, the most likely cause of fragmentation is some usage pattern that you're not used to, which only occurs very rarely and would occur over time. So how do we eliminate fragmentation? First of all, we never call free. So, this generally is the way you do memory pools. And most real-time operating systems that are used in constrained environments recognize this, and some don't even provide a malloc, a standard heap. And they only provide a set of pooled buffers. Well, when traditionally trained desktop programmers look at that and they say, where's my malloc, where's my free? And it's just a matter of they think that well, I'll just try to use these buffer pools the same way I use malloc free. And really what you need to do is define your data structures differently to work in this environment. And here are some, you need to drastically minimize the number of allocated buffers. Declare temporary buffers inside other buffers so that you have one one allocation creating space for a lot of different purposes. And be willing to waste memory. So sometimes it's often in a constrained environment better to allocate the maximum size of something and include it somewhere in another structure rather than have separate allocation. We'll get into examples of that. So what you want to do is get it down to a small number of buffer sizes. So last year, one of the things I did was rework the IoT stack. The IoT stack code allocated, I measured something close to 200 different mallocs and an equivalent number of frees. And when I reworked it into a transaction environment, which is what I'll be talking about here, it got down to 8 allocations instead of 200. And that's a doable number. You can have 8 memory pools to get things out of, but you need to completely rework how the memory is used. And a key tool that's used in embedded programming of all sorts is the transaction. Allocate one buffer to handle the entire transaction. All the strings, all the structures. Allocate one big structure that includes all those things, rather than having a small buffer here pointing to another buffer and so forth. And this way, for a typical leaf node, you can get down to a single structure that handles the entire transaction. Now this might be a large structure, and what it does is it makes it very predictable what's going to happen in the device. Either that structure is available, that buffer is available to handle the transaction, or that transaction is not going to be handled. You don't get halfway through and then find out that you can't handle it. And there might be different types of transactions that require different size buffers, but ideally there would just be one. I also am going to suggest the concept of a trace, which is, I think, my own instruction, which is buffers that need to be left around between transactions to recognize ongoing activity. And of course, there may need to be these, but again, a single trace should handle a single function so that you don't need to allocate a number of buffers to do that intermediate transaction. Now, here's what keeps us from thinking of transactions. Typically, we think of layers of a protocol. So for instance, I'm going to give an example of TCP protocol on top of UDP protocol on top of, excuse me, no, that's wrong. TCP protocol on top of IP protocol on top of the socket layer. And it would be very reasonable to, as each part of such a transition through the stack, through the kernel stack was performed, allocating a new structure. But what they do instead is allocate a single buffer, and it's called a slab typically. There are other names for it. And do what's called slab allocation. And so the slab contains all of the variables that are needed for TCP, all the variables that are needed for IP, all the variables that are needed for the socket layer, for the hardware layer underneath. So the point is when they can either allocate the slab and perform the transaction, or they can't. And so this is very well known. You can look up slab allocation on the web, and it's very much like a buffer pool. But we don't think of this because a lot of our training in computer science is to separate the layers and make the layers separate. And therefore we think of allocating buffers separately for the different layers. And this has kept a lot of systems from handling things in a transactional way. The myths, wasting scarce memory must be avoided. If memory, it seems obvious, if memory is short, don't waste it. Well, sometimes you have to waste it because in embedded programming, predictability is more important than efficiency. So the question is not how many transactions can you handle at a time, but how many transactions can you guarantee to handle at one time. So if you've allocated according to the transactional level, then you're either going to be able to handle a transaction or you're not, and you know. So here's an example of wasting strings. On the left side, you would do a malloc on the size of the string and assign it to the variable name. On the right side, the entire string is already allocated to the maximum size of the string, and no matter how large the string is, it's just going to use that structure. This is predictability at the cost of wasting memory. So in most of the time, you're going to be wasting memory, but it's a huge predictability in what you're going to do. Same thing is true of buffers for structures. Instead of allocating the structure as it is on the left side, you would allocate the structure as part of the larger structure. Again, you might be wasting the space. A transaction may or may not use temp1, the bar structure. If the transaction doesn't use it, then you've wasted that memory. But you've bought predictability. You know if the bar structure is needed for this particular transaction, it will be available, and there won't be any question about whether it needs to be allocated or not. And then the traces, again, you have to minimize the number and allocate them separately. So this brings up the concept of buffer pools, where you have an example here is if you have 3 pools of 3 different sizes. The buffer pools, if you don't know what your program, your application looks like, you might allocate arbitrary sizes, power of 2 sizes, so forth. But if you're actually defining your application, you should be able to make pools exactly the right size for what you need and parameterized based upon any code changes. With memory pools, you can guarantee the behavior of your program. You can monitor the program. Now notice when you use malloc, you very often don't know what your program's doing. How do you look into a program or monitor a program or attach parameters to it to look at how the program is behaving? You don't really know how your program is behaving. You don't know how close you are to running out of memory. You don't know how many times really you failed. By having memory pools, you can say, here, each of these sizes, let me know when each of these pools gets exhausted or when it's near exhaustion. And I mention exception handling because very often, and this was the case in IoT when I started looking at it, when an allocation fails, it just goes into the normal path, and the normal path often has mallocs that fail. And the result can be that you don't know what's going on. So it's important that the memory, the path to failure be completely able to face running out of memory in a memory pool. And one way to do that is to pre-allocate all the buffers that are used for exception handling. And again, this is wasting, because most of the time you don't have exceptions, and the buffers are sitting there. But it's better to be able to have the buffers when they're needed than to make them available to run the rest of the program. So in summary, IoT leaf nodes and some gateways will continue to be highly resource constrained due to requirements for minimizing cost, power, and maintenance. Embedded software requires explicit and careful memory handling to run reliably for long periods of times with limited memory resources. And these techniques are known and in the embedded community, and certainly when you write an operating system, you follow, just as I described with the network stack, but they need greater visibility in the IoT community. So coroutines, just mentioned briefly, a method of decomposing complex designs, and they're not very well known, even in computer science graduates. I love this quote from Don Knuth, subroutines are special cases of coroutines, so actually coroutines are the more general form, and subroutines just happen to be one way of implementing coroutines. But if coroutines are used more generally, they can provide the equivalent of threads. Now, threads are useful for decomposing complex systems. So, for instance, you could run input, process, output, and queue between each one. And, whoops, I got lost in my own, there we go. And here you would put a thread on the input, a thread on the process, and thread on the output. But very often you don't have these threads in a constrained environment. You may or may not have the threads. You may have 2 and you need 3. Same thing. So you can implement the same thing with coroutines. Still, input, process, output, with a queue in between to do the processing. And as an example of how that looks, the threads, whether it be 1 per process, but in the coroutines there'd be 1 total thread that would be running everything, but you can still organize things as separate threads. And the nice thing about this, if you look at it, is on some machines where you have threads available, you could use them. And where you don't have threads available, you would use coroutines. And the code, the actual processing code, would look the same, but you could move it between environments. So here's an example of the coroutine code. I'm not going to really spend much time on it, but basically you give control to the other processes to function, and you call them blindly. You say, here, take the thread for a little bit, and it goes, and as long as it doesn't block, it'll do all its processing and then come back. And here we have the equivalent of the lower section where the process gets called, and as it starves for input, it calls the input thread. And where it's starved, where it's constipated for output, it calls the output thread. And a single thread runs everything, but it's still a decomposed system that can be easier maintained and used in an environment where threads are available. So in summary, just say that embedded programming skills and techniques here in the are needed. And I'm not so much trying to teach you these skills as raise awareness of the importance of having team members and who understand these things so that they can be used, and the normal, that both avoids the normal programming methodologies in some cases, but it also means that you can build systems that run for long periods of time. You can actually prove, in a sense of the word prove, that a program will run forever based upon the memory that's available with proper use of memory pools. Whereas with a malloc, you just don't know. And coroutines, the ability to build systems with and without threads, I think, is tremendously valuable. And I just want to see coroutines used more often. So that's the end of the presentation. I'll point out that I've written a couple papers that describe the memory management issue. Then you're free to, those are at the end of the slides. The slides are uploaded. these point to papers that I wrote on the subject of using the memory management facilities. And are there any questions? Yes?
Can you describe a transaction as it's more in detail?
Say what?
Can you describe the transaction as more in detail?
Okay, a transaction is, I'll give an example. In IoT, a single CoAP request comes in. It's a request. It's either a post or a GET. What you do is make a single structure that is going to be able to process every issue associated with that GET. And that means that you're going to tie together a single structure of things that are at multiple levels in the hierarchy. In the case of IoT, it's providing a library, so you might even allocate space for the users processing in that structure. But you make sure that when that CoAP request comes in to do a GET or a put, that you, in one allocation, have all the memory you'll ever need to perform that transaction all the way around. I hope that's, and I didn't repeat the question, so I think the question was an example of a transaction. So, yes. Say that again.
Do you have any experience with Libmill that uses coroutines kind of emulate what the language does?
No, I'm not familiar with the use of coroutine packages. I'm actually the question was, am I familiar with Go? Libmill, emulation of the Go programming language, and no, I don't. There's a line here that I skipped, went over. No coroutine libraries needed. I mean, you can use coroutine libraries to make complex coroutines, but you can also use coroutines very easily without any sort of library support at all. You just need to keep track of who's calling whom. It's a little bit of manual work, but that's appropriate for an embedded environment. But there's nothing wrong with using libraries to help you, but I'm just saying it's not necessary. As long as that's the only, so the question is, if you made all the mallocs the same, if you made the malloc the same size and made sure it's free, then that solved the same problem. That's true if that's the only malloc. Now, if there's other mallocs, they can take you free that memory, and another malloc could use a little bit of it. And now that space is not available to the next malloc of the same size. If everything's the same size, go for it. The problem is most programs need different sizes of allocations. And then as soon as you have different sizes of allocations, all bets are off. All right, well, thank you very much for coming. And feel free to contact me if you have any questions about this. First slide. Oh, sure. This is clearly hyperbole, but go ahead and ask me your question. Well, you can also download the slides from the website. Would you, I'm a little hard of hearing. Would you state that question again?
So we have libraries that are like third-party stuff, some open source libraries and such. And they often do this memory management behind the scenes by themselves. So do you think there should be some sort of effort to change the API so that memory could actually be given to them from the outside from this memory pool?
Yeah, the question is that you don't write all the code. Very often you're using libraries, and the libraries will do mallocs behind your back. And then what do you do about them? Well, that's a good question. That's an excellent question. I think in the constrained environment, you need to look for libraries that handle memory, where if they need a memory buffer, you call them with the buffer, and they use that buffer or if they need a place to put their output, you call them with space to put that output, rather than having them do the mallocs. And I think that points to a problem that a lot of the libraries that we're trying to push into embedded programming don't do that. They allocate memory, and then they create the problems that we're trying to solve here. Very good point. I should have brought that up. All right. Thank you.